Welcome back. Last two classes, we have been discussing about one of the important NMR parameter, which is because of the internal interaction, that is chemical shift. We discussed several points about chemical shift, but still we need to understand much more because it's one of the important parameters which is used when you want to analyze the NMR spectrum. So chemical shift and couplings are the parameters which you cannot avoid. So it is better to spend a little bit more time to understand few things about chemical shifts. So let us continue today with that. And last time I showed some spectra, and depending upon the symmetry of the molecule, how many peaks we can get, and how can we get the internal area of the peak, and identify the number of protons present in each peak, everything. But when I said that different peaks are coming at different places, we must measure it. What is there? There must be some reference, is it not? If I start looking at, for example, this peak, I say this is the frequency coming at some value. What is that value with respect to what? There must be some reference for everything. So when you want to measure frequency, another, of course, you can, without any reference also you can do it. But then I'll say I measure the frequency and say this is 1000 hertz. Someone else, an X, can go and record the spectrum in a different spectrometer with a different frequency spectrometer, like I do in 500. Let us say he does in 1000 megahertz. That he can say it is the same frequency. So we need to understand with some reference, because different people can record the spectrum in different spectrometer frequencies and each may come out with a different value. It is not right. So we must have a reference. Generally, for each nuclei which you want to take, let us say NMR of proton, carbon 13 or silicon 29, tin, lead, any nuclei of your interest, there cannot be a uniform reference for all the nuclei, right? As a consequence, for different nuclei there are identified references. For example, for proton, carbon and silicon, tetramethylsilane is used as a reference, and the value of tetramethylsilane, I know where it comes. Generally it comes at a very, very high field. I tell you why later. Set that frequency as 0. With respect to that, all other frequencies are measured. So tetramethylsilane is used as a reference for proton, carbon and silicon, all the three nuclei as a reference. So without an internal, of course there are internal reference and external reference. Tetramethylsilane is always used as an internal reference. Very microscopic quantity, very minute quantity of TMS can be added to the sample, and then take the spectrum, set this value to 0 and measure your frequency. That's normally what is done. And this is tetramethylsilane. The question is, why are you using tetramethylsilane? Why not something else? If you look at this molecule, this is a tetramethylsilane. This has a highly symmetric molecule. All 4 CH3 groups are chemically equivalent. See, this CH3, this CH3, this CH3 and this CH3, all the 4 are equivalent. Of course, I have written the structure in a different way, don't worry. But all chemists will definitely looking at the molecule, they know what is the structure and they know all this because of the symmetry. All CH3 protons are chemically equivalent. In addition to that, protons within the methyl group are also equivalent. Very interesting, is it not? See, the chemical environment, electronic charge distribution at the site of CH3s and all the CH3s are same, identical. All 12 protons are chemically equivalent with identical charge distribution surrounding them. That means all 12 protons are equivalent. Remember last class we found out the peak height, and then we say that there are a number of protons are present relative to something. But individually I can say, if I take the proton spectrum of tetramethylsilane alone, because I know the molecular structure, all are equivalent, I can say there are 12 peaks in that. It is going to give all 12 protons are equivalent very strong peak because all 12 protons are resonating at the same place, remember. So as a consequence, it gives a very huge intense peak and only one peak. That's another thing. The question is, so what? Why should we use TMS as a reference? I know that you can find some other molecule which has more protons and the chemically equivalent. I don't know if it is there really. Why can't you use that as a reference? Naturally, the question will come, and the pioneers in this area have already done a lot of work, and then they have come out with the reason why tetramethylsilane, which is also called TMS, is used as a reference. First, it is soluble in most of the organic solvents used in NMR. See, what happens is when you want to study a solution state NMR, this molecule of your interest should be dissolved in a solvent. Usually they are organic solvents like chloroform, dimethyl sulfoxide, DMSO, acetone, CD3CN, acetonitrile, etc. These are all deuterated solvents. I tell you why we have to use deuterated solvent in next 1 or 2 classes. But right now you remember these are all organic solvents we use. And TMS is soluble in organic solvents. Second important point, TMS is inert and do not react with the samples. It is inert. And if you have a sample of your interest, you can be safe. Your sample will not interact with TMS. There is no reaction that is going to take place. So it is safe to use this. Secondly, it is highly volatile. It has a lot of volatility. So just open the TMS bottle in the laboratory, keep it, a big bottle of 100 ml. Within half an hour or so, you see the bottle will be empty. It will evaporate because it's a highly volatile liquid. So as a consequence, even if you add small quantity of tetramethylsilane as a reference for your sample, since it is volatile and non-reactive with your sample, it is inert, simply you can evaporate out, it will evaporate and you can recover your sample. Very easy. As I said in the previous slide, all 12 protons are equivalent, gives a single peak in NMR. Most important thing is, all 12 protons are highly shielded because silicon has low electronegativity, and that's why TMS always resonates at a very high field. Most of your NMR spectrum of any molecule is blue. Of course, I am not telling all, most of them. There are some molecules whose spectra comes beyond TMS also, if we take TMS as a reference. But majority of the cases, all spectra will come below TMS. If we take TMS as 0, it comes less than TMS. More than TMS, higher field than TMS. Less than TMS means lower field than TMS. TMS comes at very high field. Sometimes you may come across some molecules which can resonate beyond TMS, even higher field than TMS. But nevertheless, TMS is the best sample to use as a reference in proton, carbon and silicon. That's why it is widely used. I said this is for organic sample. Then you ask me a question, what should I use if I have to take protons NMR, where I have to use where I have to study samples in non-organic solvents. For example, I want to do in water. I have a biological sample, like a protein or peptide or something, which is soluble only in water, let us say. What to do? TMS is insoluble in water. Some of the biological samples have to be studied only in water. Then what to do? In such cases, for water soluble samples, for proton NMR, another reference is used called TSP or DSS. TSP means tetramethylsilane propanoic acid. This is TSP. DSS is sodium salt of trimethyl propane sulfonate, some big name. Don't worry. You remember, for proton, if you want to do in the water or any non-organic solvent, especially biological sample which are soluble only in water, reference cannot be TMS, reference has to be TSP or DSS. Okay. So different nuclei has different references, I told you. These are all three, because if you go back to this molecule Look at it, it has a silicon. All carbons are equivalent, carbon is there, all protons are there. So only 3 nuclei are there in this molecule. All the 3 are NMR active, interestingly. That is why TMS is used as a reference for NMR of all the 3 nuclei. But for different nuclei, what you will do? If I have to look for, let us say, phosphorus NMR. For phosphorus NMR, remember 85% H3PO4 is used. Okay, that's the important thing. 85% H3PO4 used for phosphorus NMR. For tetramethylsilane, tetramethyl tin used for tin NMR. Again, similar to TMS, and 4 methyl groups are there. All 4 methyl protons and let us say all 12 protons are equivalent. So that is what is used for tin. If you come to lead NMR, see, this is what we are going to use. This is tetramethyl lead is going to be used. Of course, I said for TSP. For nitrogen 15, you are going to use what is called ammonium chloride. And fluorine NMR, you use this one. Okay, CCl4, CCl3. CCl3F is what is used for fluorine NMR. So these are the important things. But then when I say we use as a reference, what is the reference you are using? Okay, we use TMS, but how do you measure this value? Remember, the chemical shift of all the protons is expressed in what is called parts per million delta. It is given as delta. Delta is nothing but frequency of your signal minus frequency of your reference divided by the spectrometer frequency. Of course, multiply by 10 to the power of 6. I tell you why we have to do this. You know the frequency of the signal with reference to frequency of the reference. Let us say I am taking spectrum in 300 megahertz. One methyl group is there, only one methyl group, and TMS is there. Both are coming at in 300 megahertz only spectrometer, but between TMS and methyl, the difference is very small. Both in the 300 megahertz, small chemical shift of the order of few hundred hertz will be there. So the difference in the frequency of the signal with respect to the reference is of the order of few hundred hertz. Whereas spectrometer frequency is in megahertz, remember. So the numerator is in few hertz, spectrometer frequency denominator is in megahertz. If you multiply that, then for example, my chemical shift of the proton is, let us say, 600 hertz in a 300 megahertz spectrometer. The difference between reference and signal is 600, and spectrometer frequency is, I said, 300 megahertz. So 600 divided by 300 into 10 to the power of 6. 300 megahertz. Megahertz means 300 into 10 to the power of 6. So remove this and this will get cancelled. You see, for example, if I use and this will go and this will go, what is going to left? 300 by 600 by 300, and you are going to get 2. So the chemical shift of Ca3 protons, which is coming at 600 hertz in a 300 megahertz spectrometer, is 2 ppm. Remember this point. We express the chemical shift in ppm. Okay. So with this, let us see further. What is the advantage of expressing this chemical shift in ppm? Remember, when you express this chemical shift in ppm, interesting thing is ppm is a dimensionless quantity. There is no unit for it. If I say chemical shift of proton is 7 ppm, it's 7 ppm, 7 parts per million, that's all. So whether you record in my spectrometer, your spectrometer of different frequency, doesn't matter. It's always same. It's a dimension. It removes field dependency, doesn't have any field dependency. That means, let us say your chloroform comes at 7 ppm in your 500 megahertz. I am going to record in my 800 megahertz spectrometer. You say chemical shift of chloroform is 7 ppm. I will also say 7 ppm because chemical shifts when expressed in ppm, there is no field dependency. It doesn't matter whichever the spectrometer you use, whichever the field you study, value is same. When expressed in ppm, it remains same. Remember that. And it requires a reference frequency, which we always use. The reference frequency is set to 0. I already said with TMS. So generally, when you want to take NMR in the solution state, this is what we do. Just to show you, go to any NMR laboratory and see what they are going to do. They take small 5 millimeter tube of nearly 10 to 12 centimeter length like this, with the different types of caps like this. Now what you will do is you will take the sample here, put inside this along with your reference, and then put it in a magnet in the NMR spectrometer and record the NMR spectrum. And the samples are always dissolved in the deuterated solvent. Remember that. If your sample is soluble in water, you can't take H2O. You have to take D2O. If your sample is soluble in chloroform, don't take CaCl3. You must take CdCl3. You must always take deuterated solvent. Why you have to take deuterated solvent? What happens if I take CaCl3? Lot of information is available. I'll tell you when you go to the parameters and experimental conditions, how to record spectrum and all those things. The important things I will discuss later. But at the moment, you remember, you have to dissolve this in a deuterated solvent, put it in a 5 millimeter NMR tube of 10 to 12 centimeter length, put it in a magnet, and then start recording the spectrum. But I said we need to take a deuterated solvent. 100% deuteration is very difficult to happen. Always, whenever you try to do, there is always some residual peak is there. Residual water peak or residual protonated solvent peak is always there. You cannot avoid that. Because I take, let us say, simple example, benzene. Benzene, if I take 100% deuterated C6D6, can I get a proton NMR? Is it possible to get proton NMR of benzene D6? No, because there are no protons. You have replaced protons with deuterium. So you can get only deuterium NMR, proton NMR you cannot do. So you must not get any signal. If you take benzene D6, you should not get any peak from your solvent. But normally, it doesn't happen like that. If you go and see the NMR spectrum, there is a benzene residual peak coming at 7.16. In bracket is an error, 16 or 17, whatever it is, you can discuss that later. Okay. So this is the chemical shift of benzene. So that means no solvent is 100% deuterated. There is always residual protonated solvent present that gives peak signal in proton NMR. You understand? Similarly, acetic acid, Ca3COOH. That means it has a Ca3 group and COOH group. There are two peaks for that in proton. Otherwise, if you take CD3COOD, 100% deuteration, there should not be any peak at all. Same way, in this list of solvents that I have given you, chloroform, if you take, again it comes at 7.26, there is one peak. And in addition to that, if you look for carbon 13, see, these are all organic solvents. Forget about D2, H2O, water. Others are organic solvents, which also has carbon. Similarly, benzene has residual carbon peak, a proton peak here. But in the carbon, what happens? You are not deuterating carbon, you are deuterating only proton. So carbon is still there. So carbon NMR is possible to record. So it is, don't get confused. This is a residual peak, but this is not a residual peak. It is a peak from the solvent. It is present. You can detect that. So these are all these solvents also has carbon peaks in the carbon NMR. For example, acetone. What is acetone? CA3 twice CO, right? So you have a CO peak here and CA3 peak here. Both are present. See, this is what happens. If you look at this, methanol, CA3OH, there are two proton signal, one for OH, one for CA3, and in carbon, you have only CA3 carbon. OH doesn't have any carbon. So that doesn't give spectrum in the carbon 39 number. So like that, these are a list of solvents where you can see residual protonated solvent peak, and when you go for the carbon NMR, directly you get carbon peak. Sometimes what is going to happen is, when you record the spectrum, the solvents what you take may not be 100% pure. There will be always some residual water peak for various reasons. We want to try to put the solvent into your NMR tube. It may be hygroscopic. It may absorb moisture from your solvent. It is more so especially in dimethyl sulfoxide, which is highly hygroscopic. And such solvents, because it has residual water, monomeric water will be there, and that gives rise to residual water peak like this. For example, DMSO peak. Then if you find a peak in a NMR spectrum taken in solvent at 3.3, it may be from your sample. But if you say I cannot expect a peak from my sample at this ppm, it could be residual water. Please remember, while interpreting the spectrum, this chart is very important. In addition to residual protonated solvent peaks, you will also get residual monomeric water peaks also present. Okay, that is important. Now, what is the range of chemical shift of proton? See, I can measure the chemical shift with respect to tetramethylserine, which is set as 0 ppm. Different nuclei has a different chemical shift range. Okay. Generally, most of the cases in proton, the range is 0 to 10 to 12 ppm, or in extreme case 15 ppm. And all your peaks of most of your molecules, when you take NMR spectrum, measure with respect to TMS, will be within this range, 0 to 10 or 12, 15 ppm. In the extreme cases, if the proton is attached to a metal, or some extraordinary cases, it can go even far down, 70, 80 ppm. In extreme cases, it can go even beyond TMS, even higher field, at -4, -5 ppm also it can come. There are exceptions. I'm not telling as a rule, it has to come between 0 to 12 or 15 ppm. Remember, majority of your molecules, the range of chemical shift of proton is 0 to 10 or 15 ppm with the TMS as a reference. That you should remember. Now, one important thing you should know. Always we express chemical shift in ppm, and then we can find out the frequency of it. We can convert ppm to frequency. If I give the frequency of the peak in a particular spectrometer, I can convert it to ppm. If you give me frequency value, you must also tell me the spectrometer frequency. You can't just like that say, hey, 2500 hertz I got a peak. Tell me it's ppm. No, I cannot say. You must tell me what is the spectrometer in which you recorded the spectrum. Then I can convert frequency to ppm. Similarly, I know the ppm value. You tell me water comes at 4.8 ppm. Doesn't matter whatever the frequency spectrometer, you tell me the spectrometer, I'll tell you what is the frequency at which water peak comes. You understand the point? So ppm to frequency and frequency to ppm conversion is very, very important. Please remember, because most of the time people make lots of mistakes when they come to me. They don't know how to convert ppm to frequency and frequency to ppm. Because they are not exposed to it. But so we should understand how to do that. Now I will give you an example. At 400 megahertz spectrometer, reference signal comes at 400 megahertz. That is, reference is TMS. Fine. My sample, I have, let us say, CH3OH or CH3CN. Only one proton is there, one particular type of proton, CH3 proton. Let us say it comes at 400, so many zeros, 400 hertz. Take the difference between these two, 400 megahertz, my plus 400 hertz here. Take the difference. What is the frequency of my sample? It is 400 hertz. Difference is very small. We saw that when you wanted to measure the ppm, spectrometer frequency, your sample frequency minus the reference frequency. Both are in megahertz. but the difference is in hertz. That's what I said. So now the difference in frequency is only 400 hertz. Now I said divide this by spectrometer frequency. Is 1 hour is 400 in a 400 megahertz spectrometer is 1 hour 1 million, or this is 1 parts per million, 1 ppm. How do you write this? If I have to write it, I have to write as 0.000001, 5 zeros, 1. That is a cumbersome process. Why we have to do that? For that purpose, to simply express this as a simple number without getting into so many decimal zeros, etc. Multiply this by 10 to the power of 6. Then this will go. You will be left with only 1. That is why we say it is 1 ppm. Are you understanding me? Don't forget confused. Now I am explaining chemical shift in ppm. The difference in the frequency is 400 Hz divided by the spectrometer frequency 400 megahertz. It is 1 over 1 megahertz, or when I multiply by this another 10 power 6, this will go, okay. And finally what you are going to see remember, this portion will go when I multiply by 10 power 6. I am left with only 1 here, and that is my ppm. So ppm value is easy to express. Now at the 800 megahertz spectrometer, the same frequency, same peak, let's say, comes at 800 megahertz, and sample comes at 8 megahertz plus 800. This is at 800 megahertz plus 800 here. What is the difference? 800 hertz. Okay. Now calculate the chemical shift. 800 divided by 800 megahertz. It turns out to be again 1 over 1 megahertz. As I said, multiply by 10 power 6. These all zeros will go. Will be left with 1. What does it mean? The same CH3CN. I recorded 400 megahertz. I got 1 ppm. I recorded 400 megahertz is 1 ppm. So, but frequency difference was 800 here, 400 there. Understand the difference? Here, from with respect to reference, it is separated by 800 hertz, my peak. In 400 megahertz, with respect to TMS, it is separated by 400 hertz. When I convert it to ppm, it is same. ppm value remains same when expressed in ppm. Chemical shift values when expressed in ppm, it remains same. It is invariant with respect to magnetic field. Whatever may be the magnetic field you record, the ppm when you express, I don't care what is your spectrometer frequency, this value is constant. Understood? Now, if I say benzene comes at 7 ppm at 400 megahertz, 800 megahertz also comes at 7 ppm. But in frequency they are different. Just now we saw frequency. So now we will try to understand what is a ppm and what is frequency. Okay, what is ppm in hertz? Just now we saw for resonating frequency of proton coming at, let us say, 400 megahertz frequency spectrometer, 1 ppm is 400 hertz. Just now we calculated that. Please remember, just now we calculated 1 ppm is 400 hertz. Same at 600 megahertz, 600 hertz, 1 ppm. In 800 megahertz spectrometer, 1 ppm is 800 hertz. Very easy. When you want to express ppm in hertz, simply you know the resonating frequency of that spectrometer, simply divide by that. You see, for example, 400 megahertz, 1 ppm is 400, 600 megahertz, 1 ppm is 600, like that you can do. Now, carbon 13, if you do the same spectrometer, what happens? Carbon 13 has gamma 4 times less. In the same spectrometer, 400 megahertz of proton, carbon comes at 100 megahertz. Then what is a 1 ppm of carbon? Remember, it is not 400, it is 100 hertz, because the resonating frequency of carbon is 100, whereas that of proton is 400. So proton ppm is 400, 1 ppm, whereas carbon 1 ppm is 100 megahertz. Similarly, at 600 megahertz, carbon comes at 150. 1 ppm is 150 hertz. Same way, carbon resonates at 200 megahertz. The 800 megahertz spectrometer, 1 ppm in proton is 800, whereas in carbon 13 the same spectrometer, 1 ppm is 200 hertz. You understood the point. Now ppm to frequency conversion and interconversion, you have to do like this. Okay, where what you do is ppm, if you want to convert the frequency, you simply multiply by the resonating frequency of the nucleus. Remember this point. If I want to know ppm, I have to convert it to frequency, multiply by resonating frequency. Let us say I have chemical shift of 7 ppm for chloroform. In 400 megahertz, it is 7 into 400, 2800 hertz. The same 7 ppm in 1000 megahertz, 7 into 10, so it is 7000. So like that, you should remember how to convert ppm to frequency. For ppm to frequency, you have to multiply by the resonating frequency of the nucleus. Now, converse is what to do. If you want to convert frequency to ppm, simply divide by the resonating frequency. If I say the resonating frequency I got is 2500 in a 500 megahertz spectrometer, what is the ppm? 2500 divided by 500. How much? 5 ppm. You understood the logic? So simply this is the important point you must remember. This is what most of the people who come to me make mistakes. Don't make mistakes. Please remember, ppm to frequency conversion, you have to multiply by the resonating frequency. From frequency to ppm, divide by the resonating frequency. Okay? You can do number of such example. Let us say ppm and frequency interconversion. I'll give you one or two examples today before stopping. And a 600 megahertz spectrometer. Okay? Carbon, that proton resonates at 600, carbon resonates at 150, nitrogen resonates at 60.8. Why? We have been discussing because gammas are different. This gamma is almost 4 times smaller, this is almost 10 times smaller. Same spectrometer, 600 megahertz. Proton comes at 600, carbon comes at 150, nitrogen comes at 60. Remember this point. Now, I'll ask you a question. What is 2 ppm in proton? 2 into 600. You have to multiply by frequency to convert ppm to frequency. It is 1200. Are you all with me? Now I want to convert 5 ppm of proton to frequency. 5 ppm in 600 megahertz is 5 into 600, 3000. Similarly, 10 ppm, 6000 hertz. Now, on the same 600 megahertz spectrometer, I have a peak at 1800 hertz. What you will do, how many ppm is this? Divided by 600, it is 3 ppm. Similarly, at 2400 hertz, I have a peak, divided by 600, will get 4 ppm. At 3600 hertz, you have a peak, divided by 600, you have a peak at 6 ppm. So this way you can convert between ppm and frequency. Interconversion is possible. I'm trying to say these are all important things to understand how to convert ppm to frequency and etc. Now I'll take another simple example. On a 600 megahertz spectrometer, carbon comes at 150, nitrogen comes at 600. Now what is 20 ppm in carbon here? Remember now it is 150 is the megahertz in the same 600 megahertz spectrometer. So 20 ppm in carbon is 20 into 150. Don't multiply by 600 now. Don't get confused. That is a proton. Now the carbon resonating frequency is 150. So 20 ppm of carbon is 20 into 150, 3000 hertz. Fairly simple, right? Don't get confused. Make no mistakes. Please remember this. 50 ppm, 50 into 150, 7500 hertz. Same 100 ppm of carbon, 100 into 150, 15,000 hertz. Okay. Now, same way you convert it back. I have 1500 hertz divided by 150 megahertz. 150 because it is a 600 megahertz. This is 150 the resonating frequency. You have 10 ppm. Take 5250 Divided by 15, you get 35 ppm. So ppm to frequency, I have given a number of examples. ppm to frequency conversion, frequency to ppm conversion. Please remember these things is very, very important for understanding. Okay. So what I'm going to do is I'll stop for the day. I told you something about, we are discussing a lot about chemical shifts. Today we discussed about measurement of the chemical shift in ppm, ppm to frequency conversion, so many references what we use for different nuclei, and what is a ppm, everything we understood. I guess I'm taking all of you are with me. Hope you are all with me. You are catching up with what I'm telling. Please don't forget, these are very important points. I'm stressing again and again because these are all fundamentals, and especially when I'm giving this course for chemists, you should not make mistakes because you use this NMR spectrum almost every day in your research. So you should understand this concept. So we'll stop here. We'll come back and continue later.